Hi everyone, welcome back to my channel. Today we're going to talk about another problem which is named as, is it your birthday? Well, in this problem we have a gathering of people, and what we want to find out is the minimum number of people n such that if we pick two people randomly, then the probability of them having the same birthday is actually greater than 50%. Okay, so what is really going on here? Before we get into that, if you've been liking my content so far, please do subscribe to my channel, and also like this video, and also give your comment about your experience with the channel so far. I would highly appreciate it, and it also motivates me a lot to do more videos. Okay, so here what's happening is we have a gathering again, and as we want to basically keep increasing the number of people to the extent the minimum amount of people we want is so that if we pick two people randomly, the chance that they have the same birthday is actually greater than 50%. Now, a few things here, a few clarifications. When we say same birthday, we only care about date and the month. We don't care about the birth year, okay? So as a result, if we assume 365 days in a year, this gets simplified, and we can just say if two people, let's say, have the same birthday, then in that case, they gotta have the same day of the year. So if I just say, let's say, day of the year starts with 1st Jan, let's say this is 1st Jan here, and then 2nd Jan, and so on, and this is 1st Feb, but you see this is the 32nd day, this is not 1 again, and similarly we just go all the way till 365. You know, it's simple, just 365 days a year. If two people have the same birthday, then basically they should have the same number of this year. So if, let's say, somebody had 2nd Jan, then their birth date is going to be 2 for both the people, okay? And obviously, if somebody has 1st Jan, it's going to be 1. But if somebody has 1st Feb, it's got to be 32. In that case, they do not have the same birthday. Okay, so I hope this clarifies some of these confusions that can arise. Okay, the second thing is basically to make this problem, give some structure to the problem, you could just number the people from x1 to xn, as it has been shown here. You know, x1, x2, all the way till xn. And then also, because, you know, we're trying to find a computer probability of two people randomly picked having the same birthday, we can just simplify it and say it as P. Okay, so this is more like a short form given here. Okay, the short form. Okay, now if you've done this problem before, or if you have an idea that you can do it, now's a great time to pause the video and try to give it a shot and try to solve it yourself. And we'll be back shortly. All right, so I hope you give it a shot and you came up with an answer. In case you could not, that's perfectly fine. We'll shortly give a hint and then give it another shot from there, okay? And if you got to the answer, that's great as well. Just hang out till the end of the video so that to confirm if your answer was right. All right, so the first hint here is instead of solving for P, which is, you know, two people randomly chosen having the same birthday, solve for the opposite. So what I mean to say is in the question, you know, we want this probability right here, we want this probability to be greater than 50%, as we had indicated here. If you can see, this is what we're looking for, to be greater than 50%, and this is the same thing. So what we want is, our objective is, if I have to say objective, my objective is P has to be greater than half, okay? Well, I can also achieve this objective if I look at the opposite. So what is the probability two people randomly chosen do not have same birthday? Okay, so we want probability. We want to find out the probability of two people randomly chosen to have not the same birthday. Well, if you see, it's basically nothing but P bar or P complement. Okay, and using the simple fundamental, you know, some of the theorems of probability we have, if there is an event A, and the probability of it's happening is PA, then if you consider both the events, whether it happens or it doesn't happen, because A bar is nothing but the probability that event A doesn't happen, then if you add up these probabilities, it's got to be 1, because either event A can happen or it cannot happen. So if I combine the chance that it happens via this, and if I also add up the chance that it doesn't happen, it has to add up to 100%. Okay, so I'm going to use this and I'm going to modify my objective here slightly. The modify objective is P bar probability should be less than half, because this is exact opposite of you know, what we wanted here. Okay, and if you have to simplify, p plus p bar has to be equal to 1 because the theory, because of the property I just showed. So therefore I can just say the probability of 1 minus p has to be less than half. This is what you're looking for, right? So this is the modified objective. So if I can solve for this, you know, it could be an easier way to do this problem. So now pause the video and try to give it a shot yourself and see if you can get to the answer. Okay, so I hope you got to the answer, but in case not, that's perfectly fine. In either case, just hang out till the end of the video to see how we solve this problem. Okay, so now I'm going to use some very fundamental theorem or very fundamental formulas of probability. If I have to compute, let's say, a probability of any event, let's say A, then I say, look at all the favorable outcomes. And when I say favorable outcomes is basically when all the events or all the outcomes when A happens, and divide by basically all possible outcomes. Okay, and of course these all possible outcomes include the outcomes where A happens or A doesn't happen, either ways. Okay, so in this case, let's try to find out what are all possible outcomes here. We know that we had named people from x1, x2, all the way till xn, okay? And these are basically people in the gathering. And each person, if I look at xi, each person can have their birthday from 1 to 365 included. So xi's birthday can be anything. And of course, I have to mention that it's nothing but a positive integer. That's a short mathematical form. Ignore it if you don't understand it, but what I mean to say is simply that their birthday number can pick up any number from 1 to 365, okay? So that means they have a possibility of having 365 options, okay? Now, first person can have a birthday from anywhere from 1 to 365, so there are 365 options. Now, the second person, similarly, it's independent. They can be born, they're not related to each other, so that's the assumption here. Again, they're not from the same family, but they can be born on any date of the year, and in case they were of the same family, it's not going to make any difference in terms if you exclude the birth year. Okay, so again, coming back to the point, second person also has 365 options because they have the, you know, God has the freedom to send them to Earth on any given day amongst the 365. Similarly for the person 3, and so on. So for n people, you see, we have each person has 365 options. And using the fundamental principle of counting, which basically says we're looking for all the n people in this gathering. It's not just one person. So we will multiply them. So it's going to be 365 times 365, all the way till 365. And that's going to happen n times. Okay. So therefore, all possible outcomes here are 365 bar n. Okay. These are all the possible combinations of n people having their birthdays in this gathering. Okay. So I hope this makes sense. This is all possible outcomes. Now that's an important, you know, answer. I'm going to remember this, but it doesn't give us the full answer because the full answer is right here. We need now the favorable outcomes. So we have this, but we don't have this. Okay. And like we said, our modified objective is to find p bar or the probability or the favorable outcomes where people do not have the same birthday. And it's easier to find this way, and you'll see why. So let's just try to figure out what is going to be the situation in which nobody has the same birthday, because we want no people, any randomly chosen, to have the same birthday, okay? So when is this possible that they will not have any, there's no possibility that they will have the same birthdays? Well, it is possible, let's say if you have, again, xn people, right? These are the people. If I say, let's say x1 has picked up any day, let's say, you know, x1 is the first person, so you could just give him any birthday and 365 options again for this person. And let's say this had 1st May, okay? Now, there's naturally, if there's another person in this gathering that has 1st May, then there's a chance that if you pick two of these people, then they can have the same birthday. And we're looking for a probability where no two people have the same birthday. If you remember, if you go back here, no two people randomly chosen to have same birthday. Okay, so therefore it's important we make sure that no two people have the same birthday here. So what do? We make sure that nobody else in the gathering has 1st May. So therefore, the second person can choose any birthday except for first mate. So they have 364 options. Similarly, if I have x3, they will not be able to choose the first two birthdays, which has been chosen by x1 and x2. So naturally, you have 363 options now. And similarly, all the way, if you go here, xn is going to be 365 minus n minus 1. Okay, and you can check if you fill in the value of n for n is equal to 2, you naturally see it's 364. So this looks good. Now, again, these are n different people. So using fundamental principle of counting, we have all favorable outcomes. So favorable outcomes count is basically 365 times 364 times 363 all the way to 365 minus n minus 1. Okay. So again, this is an important answer, and again, it's a variable. There's a variable n here, so it just depends what n we feed, and then we're gonna get the answer. That's okay. That's equation 2. Now let's just take a quick look. How far have you come? So we have computed all possible outcomes, and we were looking for this probability here. We have all possible outcomes here, and we also have favorable outcomes here. Okay. And again, our objective is to make sure no two people have the same birthday. So we can compute the probability. And this probability is going to be p bar. It's probability two people randomly chosen not have same birthday. Okay, so simply we divide the favorable outcomes by total outcomes. So this is equation 2 by equation 1. And if I have to compute it like this becomes equal to p bar equal to 365 times 364 times 363 all the way to 365 minus n minus 1 divided by 365 to the power n. Okay. Now you may be thinking, hey, what are we doing here? We were supposed to find out number of people, and where does it lead to? Well, let's go back to our former equation that we had computed. Here's our friend, which is 1 minus p has to be less than half. And it came from the fact that we were looking to have this objective. Now, because I've directly computed p bar, so I can just directly use this, I want to make sure that this probability, no two people having same birthday, to be less than 50%. And that is what I'm going to use now. So here, what we want is to satisfy objective. P bar has to be less than half. This implies 365 times 364 all the way till 365 minus n minus 1 upon 365 to the power n has to be less than half. Okay, now at this point of time, I would say the interviewer should definitely let you use calculator, because you know this is not possible to do it unless you're Shakuntala Devi or a supercomputer mind. But anyways, let's try to just give it a shot to see where we are. So if we just had one person n, it would not make sense because we need two people here. So I would say it's probably not well defined for n is equal to 1 as per problem. For n is equal to 2, let's see what we get. So let's say just two people in the gathering. Let's say what's the probability of them having not same birthday, and is it less than 50% or not? Okay. So again, 365 times, if I put n is equal to 2, I directly get times 364 divided by 365 square. Okay, and this comes out to be 364 by 365. And now you see this number is actually very close to 1. It's not exactly, but it's quite close to 1, right? So it's definitely greater than, it's definitely greater than half, and it's not less than half for sure. So let's see if we find something for n is equal to 3. So if we see n is equal to 3, what we get is 365 times 364 times 363 upon 365 cubed. And this will become equal to 364 times 363 over 365 times 365. So if you see, there are two numbers here, 364 by 365 and 363 by 365. And both these numbers are actually less than 1. So if you actually multiply two numbers which is less than 1, say 0.9 times 0.9, you don't get a bigger number, right? You actually get 0.881, which is what you see here. The number is going to be even lesser than one of them. So it's going to be less than 364 by 365. And the reason is because 363 by 365 in itself is a number less than 1. So you're reducing this number further. But it's pretty sure that it's got to be greater than, this number is still got to be greater than half. Because, you have still two numbers. If I had to just clean up a bit. You still have two numbers here, 364 by 365 and 363 by 365, which are close to 1, and their product is definitely got to be greater than half, and you can check it manually as well. So this is also going to be greater than half. Now, if you keep on doing this process, what you see at n is equal to 23, you actually come up with a product, or with the answer is going to be actually less than half for the first time. So 23 is the right number. So 23 people in the gathering, and then you will have a chance that any two people, the probability of any two people not having same birthday is less than 50%. And inverse is going to be, because p bar half is going to be less than half for n is equal to 23. This would also imply p is actually greater than half for n is equal to 23. Because again, p was actually nothing but 1 minus p bar. As we said, it was just a complement of the event. Okay, so I hope you got the answer right. The answer is 23. And in case you liked the problem, you found it actually gave you a good exercise of your mental muscles, please do give it a like to the video and also comment about your experience. And again, see you next time. Thank you very much for your time, and thank you for watching. Take care.